Good morning dear students, myself Sachin S. Pawar and I welcome you to my 6th video on Unit 5 States of Matter, Gases and Liquids. To begin with, I should tell that we have so far finished Boyle's law, Charles' law and Gay-Lussac's law, their mathematical interpretations and certain derivations. Now in today's class we will move on to study Avogadro's law and the application part of Avogadro's law, combined gas law. So let us begin with Avogadro's law. Avogadro's law. Okay, so when I go for a statement of Avogadro's law, the statement of Avogadro's law comes like this: equal volume of all gases, equal volumes of all gases under similar conditions of temperature and pressure, similar conditions of temperature and pressure have equal number of gas molecules. This is a statement. The statement is equal volume of all gases under similar conditions of temperature and pressure have equal number of gas molecules or contain equal number of gas molecules. Let us learn this, let us understand this. Suppose I have two containers. Okay, in this container I take say equal volumes I should take. So I'll take say 22.4 liters of oxygen gas and here I'll take 22.4 liters of nitrogen gas. So I have taken equal volume of two gases. We have to maintain same temperature. The temperature is, say I maintain a temperature of 0 degrees Celsius, that is 273.15 Kelvin, and a pressure say I measure as 1 atmosphere, that is 101,325 pascals. So I have equal volumes of two gases under similar conditions of temperature and pressure. Then both these containers should have equal number of gas molecules. That is a statement. So here if I check it, purposely I have taken a condition which is known as the STP, standard condition, old standard condition. We will come back on that. Here it consists of Avogadro number of particles, that is here we have 6.022 into 10 to the power 23 oxygen molecules, and in this container also you will find there are 6.022 into 23 nitrogen molecules. So just see, equal volumes of all gases under similar conditions of temperature and pressure contain equal number of gas molecules. This is Avogadro's law. So if you just see the experiment in this particular Avogadro's law, if you just concentrate on, then you will find two things are kept constant, that is temperature and pressure is kept constant, and the variables are volume and number of moles. Number of moles means molecules. You know, 1 mole is Avogadro number of particles, so number of moles. So and here as says that if volume is fixed, then the number of particles are fixed. That means volume of the gas molecule is directly proportional to number of moles. This is equation 1 of Avogadro's law. So at constant temperature and pressure, volume of the gas is directly proportional to number of moles of the gas. That is the statement number 2 of Avogadro's law. If you remove the proportionality constant, then I can write volume as constant into N. and if I take n on this side, it becomes V by n is equal to constant. V by n is equal to constant. So, according to the Avogadro's law, I have got another statement: at constant temperature and pressure, at constant temperature and pressure, the ratio of V by n is always constant. That means V1 by N1 is equal to V2 by N2. These are the V1 and V2s, and N1 and N2s are for two respective conditions, and we are going to solve some problems related to this. So, this completes Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law. Okay. Now, in this Avogadro's law, I have taken one condition that is known as STP condition. Here, fixed volume of the gas. So, can we fix the volume? Can we fix the volume if the conditions of temperature and pressure are fixed? So, here scientists have discovered or restricted our science into three main standard conditions of temperature and pressure, and those standard conditions of temperature and pressure are known as STP conditions. STP conditions. What do you mean by STP condition? The STP condition is the condition of the gas condition at which we have a standard temperature and a standard pressure. Okay. In olden days, temperature used to be given in terms of degrees Celsius. Now it is given in Kelvin, and pressure can be given in atmosphere or in bar or in pascals. We can give. There are 3 units for temperature. 2 units. There are 3 units for. Temperature. 3 units for pascals. Pressure. The conversion factor for these we shall see. 1 atmosphere is equal to 10 to the power 5. 1 atmosphere. If I say, then the conversion factor is here 1 atmosphere is 101,325 pascals, and when I say 1 bar pressure, 1 bar is 10 to the power 5 pascals. You also know the conversion factor. Fahrenheit is not oftenly used, so 0 degree Celsius. Degree Celsius can be converted into Kelvin by just adding 273.15 to that. You will get so many kelvins. So, these conversion factors need to be remembered. Let us go for different STP conditions. So, when I say STP condition, we have fixed values of temperature and pressure. Temperature, old STP conditions, and we have one more STP condition which is now oftenly used, that is new STP condition. Then we have SATP condition, and we have one more condition which is known as NTP condition. Let us see them one by one. Now, when I say STP condition, the temperature is taken as 0 degrees Celsius. So, if I just convert into Kelvin, it becomes 273.15 Kelvin, and a pressure is taken as 1 atmosphere. So, that conversion becomes 101,325 pascals. This was old STP condition. So, this condition was to be considered as standard condition of temperature and pressure. Standard condition of temperature and pressure. Standard conditions of temperature and pressure. In new terminology, the pressure is expressed in terms of bar. So, the temperature remains the same, 273.15 Kelvin, but the pressure is changed to unit of bar. So, 1 bar, and 1 bar in Pascal is 10 to the power 5 pascals. So, this is STP condition, new STP condition. SATP, in this word A stands for ambient. SATP, sorry, I just did a mistake here. It is SATP. SATP condition. SATP condition. What is SATP condition? Standard ambient temperature and pressure. Standard ambient temperature and pressure. And if I just say the temperature is taken as 25 degrees Celsius, which is if I add that, that becomes 298.15 Kelvin, I guess. And a pressure is taken as still 1, okay, pressure is taken as 1 bar, and that is 10 to the power 5 pascals. Okay, so these are STP conditions and SATP conditions. NTP stands for normal condition of temperature and pressure. Normal condition of temperature and pressure, and the normal condition is taken as 20 degrees Celsius, and that is I think 220 plus 273 is 293.15 Kelvin, and the pressure is taken as 1 atmosphere, and that comes out to be 101325 pascals. Okay, so these are different STP conditions, old STP condition, new STP condition. This is SATP condition. Let me rewrite it for you. Okay, SATP condition, SATP condition, and so on. STP stands for standard conditions of temperature and pressure, the condition at which there is a standard temperature and standard pressure. Old standards were 0 degree Celsius and 1 atmosphere. New standards are 0 degree Celsius and 1 bar pressure. Okay, so when I say standard condition of temperature and pressure, now if you apply Avogadro's law, equal volumes of all gases under similar conditions of temperature and pressure should contain equal number of molecules. So we have, for these standard conditions, we have fixed volume, that is known as molar volume. Molar volume means the volume occupied by the gas, volume occupied by molar volume. Molar volume is the volume occupied by the gas volume occupied by 1 mole of gas. Molar means 1 mole. 1 mole of gas. 1 mole of gas at STP, at standard conditions of temperature and pressure. And since there are 4 such standard conditions, you are expected to by heart the molar volumes at these conditions. The molar volume at old STP condition is 22.4 liters per mole. So for 1 mole the volume is 22.4. For STP new condition with 1 bar as a pressure, it is 22.7 liters per mole. SATP condition, it is 24.8 liters per mole, and NTP it is 24 liters per mole. So these are standard volumes, molar volumes. You have already learnt about molar volumes in PUC first year unit number 1. I am again recalling it. Molar volume, the volume occupied by 1 mole of a gas at STP. So volume occupied by 1 mole of a gas at STP, if I say it is old, that is 0 degree Celsius and 1 atmospheric pressure, it is 22.4 liters. Volume occupied by 1 mole of gas at standard temperature of 0 degree Celsius and a pressure of 1 bar is 22.7. And volume occupied by the 1 mole of a gas at 25 degrees Celsius and 1 bar pressure is 24.8 liters. These are approximate figures. The actual figures are not necessary. Approximate figures are sufficient to understand, because we have learnt what we know as significant figures. We can approximate the large figure into required number of significant figures. So 20 degrees Celsius NTP, 1 atmospheric pressure, the molar volume will be 24 liters. This is regarding STP condition. This is very, very important for your annual examination as well as competitive examinations, for solving problems where pressure, temperature and volume, pressure, temperature and volume are correlated. Fine. This is regarding STP condition. So Avogadro law gave us STP condition, molar volume. So you know what is molar volume and STP condition. With this, let us move on to the application part of these laws. So far we have seen 4 laws: Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law. So with this application, we will move on to the first application of that, that is the equation of state, derivation of equation of state. Equation of state. Equation of state. We will go for equation of state and derivation of combined gas law. combined gas law. Okay, let me first finish equation of state. Equation of state is also called as ideal gas equation. Ideal gas equation. Let me write the values here. Let me write the equation itself. The equation which right now is available as PV is equal to nRT, where pressure, volume, number of moles of gas, R is constant, T is temperature, are correlated by one equation. This is called ideal gas equation or equation of state. Combined gas law correlates between two conditions of different pressure, volume and temperature, and that is P1 V1 upon T1 is equal to P2 V2 upon T2. We will be deriving these equations. Let's derive. So this is one condition of pressure, temperature and volume, and this is another condition of pressure, volume and temperature. Whatever may be the pressure, volume or temperature, let's check that. Let's check that. Okay, so let's move on to ideal gas equation derivation. Now in the ideal gas equation we have pressure, volume, N, R and T. So R you forget about, R is called as universal gas constant. What is that we shall see, but we require pressure, volume, N and T. So search for those gas laws which contain these terms. Containing these terms, pressure, volume. Pressure, volume means we know it is Boyle's law. Okay, then volume and temperature, then you know it is Charles' law. Then you require number of moles, then you have to go for Avogadro's law. So Boyle's law, what is that Boyle's law? What is constant here? At N is equal N and T constant. For a fixed amount of gas at constant temperature, PV is equal to constant. We know this equation. Let me put it as 1. Charles' law, we know that at fixed amount of gas at constant pressure, volume upon temperature is constant. That we know from our previous studies. And Avogadro's law is at constant temperature and pressure, volume upon number of moles is kept constant. This is the third statement which I have. And if you would like to combine these equations 1, 2 and 3, if you combine equations 1, 2 and 3, see what am I going to get is PV by NT is equal to a constant. This constant is referred to as universal gas constant R. Universal gas constant R. We will derive the value of this R in a short while. So here I am getting an equation PV is equal to nRT. This is equation of state for n moles of ideal gas. Equation of state for n moles of ideal gas. Okay, for n moles of ideal gas. So this is regarding the derivation of ideal gas equation. It could be a 2 marks question, they can ask you. Okay, with this let's move on to discover combined gas law. So for this I need to just get rid of this thing. Okay, I'll just remove this. I don't want this. Okay, now for combined gas law, you see only pressure, volume and temperature are related. So I need just pressure, volume and temperature means I simply need 2 laws, that is Boyle's law and Charles' law. I simply need Boyle's law and Charles' law. So I'll just take Boyle's law and Charles' law with me. Okay, so copy, paste. So I need Boyle's law and Charles' law. So I have Boyle's law and Charles' law. Okay, so I'll just get rid of this unwanted stuff. Okay, I want Boyle's law and Charles' law. Now this Boyle's law and Charles' law need to be combined. So if you say combining equations 1 and 2, combining equations 1 and 2 implies what it implies? It implies PV by T is equal to a constant, and this is what is the combined gas law statement. When pressure, volume, temperature all are varied, then it says that for a fixed amount of gas, the ratio PV by T is always constant. That means if I just take two conditions of pressure, say P1, V1 volume and T1 temperature, and two conditions, second condition say P2, V2 and T2, then this ratio should be always constant, and I got the equation. This is the combined gas law. We will be using these two equations for solving problems. So I have told you Avogadro's law, its application for STP condition, and then derivation of ideal gas equation, also called as equation of state, and combined gas law. Let's move ahead in the last part of this today's class, that is, here we will derive the value of R. Okay, deduction of, it could be a 2 marks question again in the examination, deduction of value of R in SI unit. Derivation of value of R, derive the value of R in SI unit. It is a universal gas constant. Let us try to do it. Okay, now value of R we want means I need to search for the equation which has that R value, and that is equation of state. So equation of state for n moles of ideal gas, I know it as PV is equal to nRT, where pressure, where you know P is pressure, right? You know P is pressure, V is volume, T is temperature, and R is constant that I have to find out. N is number of moles. Of gas. Okay, let us take 1 mole of gas. Let we take N value as 1 mole. So 1 mole of gas. So it is 1 mole of gas. Then 1 mole of a gas has a fixed volume at a given condition of temperature and pressure. You know STP conditions. So we can use these STP conditions, we can find out. I know STP conditions. So STP condition, the pressure, will take old STP condition or new STP condition will take. It is 0 degrees Celsius temperature, that is 273.15 Kelvin. Volume we will take it as 1 bar, again in SI unit it is 10 to the power 5 pascals. Sorry, not volume, I'm sorry. Temperature is 0 degrees Celsius, that is 273.15 Kelvin. Pressure will take it as 1 bar, that is 10 to the power 5 pascals. So at fixed temperature, at these conditions, volume is fixed, and the volume, to be precise, it is 22.710981 liters per mole. Now here SI, here you see the SI units are there. Pascal is the unit we have taken for pressure, liter we have taken the unit for volume, Kelvin and mole, these are the units. Here liter I cannot keep it. You know 1 liter is 10 to the power minus 3 meter cube. Meter cube is the SI unit of volume. So this is coming to be 22.710981 into 10 to the power minus 3 meter cube. Am I right? Okay. Right. So Kelvin is SI unit, mole is SI unit, and rest all is SI unit. So we can write it. This implies I want to find out the value of R. So R will keep it on one side, rest all I will transfer to the other side. It becomes by NT. So this becomes pressure. Pressure is 10 to the power 5 pascals into volume is 22.710981 into 10 to the power minus 3 meter cube divided by 1 mole into temperature is 273.15 Kelvin. So I have got the value substituted with units. So that comes out to be. So I just need a calculator. So I'll just go to the calculator in my computer. So, or if you have a calculator, you can just open the calculator, and I just have to use the calculator here. So for calculator use, I'll just have to say 10 raised to 5, see 10 to the power 5 into 10 to the power minus 3, log a to the power x minus a to the power b, 5 minus 3 is 2, 10 to the power 2 will remain, 10 to the power 2 will remain in the numerator, 10 to the power 2 will definitely remain in the numerator, that's fine, okay, fine. Next, okay, next 10 to the power 2 is remaining, so I need a calculator. So what I'll do is 22.710981 divided by 1 I need not mention, divided by 273.15. So when I do that, it comes out to be 0.08344, 3144 into 10 to the power, see this is, I have 10 to the power, so this becomes 10 to the power 2, and this division becomes this, so unit will become Pascal meter cube per mole per Kelvin, Pascal meter cube per mole per Kelvin. Now what is Pascal? Now we'll go for basic units. Let us have a basic unit for this. So I'll just transfer this a bit downward here. So using these equations, we have got the value of R. We have got the value of R as so 10 to the power 2. So if I want to remove this 10 to the power 2, I'll write this in scientific notation. The decimal point will shift it to the right hand side by 2 decimal points. It becomes 8.314. So we'll just get rid of this 4. If we remove it, remains 4. It is Pascals meter cube per mole per Kelvin. Okay, now here, okay, the rest all I'll just cancel it. Now I don't want this. Okay, now Pascals. Okay, Pascal is a unit of pressure. We know Pascal is pressure. Okay, pressure is Pascal. It is force into displacement, and force into displacement is Newton into force. Force acting per unit area. Force acting per unit area is Pascal. Pressure means force acting per unit area. Force acting per unit area. So force acting is Newton divided by area is length into breadth, that is meter square. So Pascal is Newton per meter square. We know this. Okay, so if I substitute this, then it becomes 8.314, that is R is equal to 8.314 Newton. Okay, I'll write it Pascal is Newton per meter square, meter cube, per mole, per Kelvin. So I have just replaced Pascal by Newton per meter square. Now meter square raised to this becomes I'll get R value here. R is equal to 8.314 joules. Newton m raised to minus 2 plus 3 is Newton meter per mole per Kelvin. Now if you just see Newton meter is the SI unit of, it is the SI unit of work or energy. Work or energy. Work is force into displacement, and we know force is Newton, displacement is meter, so work is referred to as joule. So this is Newton meter is joule. Newton meter is joule. So I will get this as joule. So the value of R in SI unit becomes 8.314 joules per Kelvin per mole, or per mole per Kelvin. This is the SI unit value of R derived for you. There are various other units also expressed in different units. We can easily convert these units into various units as per the requirement, and we can remember that. So that's all for today's class. In the present class, we have seen Avogadro's law, its mathematical forms, application of these laws for deriving equation of state, PV is equal to nRT. We have derived the value of R, and then we have also derived the combined gas law. Thank you. I'll stop here.